Hello and afternoon. Thanks for showing up. We're going to be talking about TDI scanning microscopy today, and hope you enjoyed the talk. Let's get started. So we're talking about high throughput microscopy. And when you do high throughput microscopy, there's two basic ways to go about it. One is move, stop, acquire, which we refer to as sequential field imaging. And the other is TDI scanning imaging, and they're really quite different. In the upper plot here, we can see how sequential field imaging takes place. We illuminate the sample, and during that time, the image is integrating on the camera sensor. When the integration is complete, the lights go off, and under the cover of darkness, we race to the next field of view, during which we download the image, and then it's rinse and repeat. The key issues there are to move really fast and hold really still, and our motion stages do a pretty good job of that. A very different approach is TDI scanning imaging, the topic of today's talk. And in this case, motion is not move, stop. It is continuous scanning down what is called a swath. And at the end of the sample, we index in the next axis and then reverse direction. And so it is continuous imaging on the fly. There's no downtime for motion. And so in this case, we typically accelerate to a constant velocity and begin firing triggers, which form the basis of TDI, and we'll see that in a moment. In fact, Mike here has a very nice animation for that. Here we have sequential field imaging in a sort of a serpentine pattern, and here we have TDI imaging. You may notice that the TDI imaging finished before the sequential field did. It is a higher throughput technique, but it also requires that you master a few special skills to get it all to work. So how does it work? It's based upon what was originally charge-coupled device, CCDs. And in CCDs, the appropriate metaphor is that of an open field filled with buckets. A cloud comes over and it rains. The raindrops are photons. Metaphors are lies. So, the raindrops are photons, and the water that accumulates in the buckets are the photoelectrons. And the only trick once the right amounts of water have occurred in the buckets is how do you measure how much water is in each bucket? And traditionally, this was done by taking the water in the bottom right bucket here and pouring it into a reed device at an A to D converter. And at the moment that that bucket pours, every other bucket in that row pours one to the right. And then when the last, and this happens over and over and over again, and when the last bucket is emptied, then all of the buckets pour down into the next row at once. And that is done by an electrical signal called a vertical transfer. Now, that's a little bit on the slow side because we have the bottleneck of this one A to D reader here. And so here is current state. And in the current state, instead of having one charge read amplifier and one A to D converter, we've got, in this case, 10. But in real devices, you're about to see, that becomes 16,384 or 32,768. So we'll get to a little more attention later on the importance of the digital signals that cause these vertical transfers. They're very important, and they're generated by the encoder on the stage system. But, and here, by the way, is a complete microscope. We have an objective, a tube lens, and the sensor. But with that, let's take a look at some of Teledyne's latest real hardware and go a little deeper into beyond the bucket metaphor.
Thank you, Kevin. I'm Mike Kadour with Teledyne. Very excited to partner here with Kevin from Dover to talk further about the TDI technology. and some of our latest products. So this here that I'm holding, you can see zoomed up on the slide here, you're looking at the sensor, the die of one of our latest TDI devices. And I just want to kind of draw your attention to what's actually happening within the silicon, how this technique actually works in practice. The top area here where you can see those bands, these are the TDI arrays. In this particular device, we call this our Linea HS2. We actually have multiple arrays. So Kevin showed you a picture of one array. Pack many of those in. That facilitates a variety of different, perhaps multiplexed imaging modes or summing, a variety of ways you can view it. You can see that there's multiple arrays sitting in the device. On the silicon as well too, we have the drivers to move those charges. And then the majority of the silicon is occupied by the 16,000, in this case, ADCs that are driving the signal. There's some natural challenges that come up when you're trying to use this technology for imaging. And I want to really focus today on how it impacts image quality and the types of technologies to boost things like contrast in an image. So I'll make reference to the modulation transfer function as just a shorthand for how crisply is the device representing contrast in your image, particularly at those higher spatial frequency contents. Does it faithfully reproduce those signals, or is there some degree of blur or anything else inherent with this type of technology? The first part that we've got to kind of draw your attention to is a question you might have is those buckets are discrete, but the moving rain, as Kevin was describing, that's continuous. Your object is not stopping moving, and you have a set number of buckets. So as I pour bucket to bucket, I'm representing this here in a microsection cross-section of these pixels. What happens when the object is sliding past each of those discrete pixels? Well, for a period of time, I'm collecting in one, and then I'm collecting in the other, and then I move the charge really quickly all at once. There's a little bit of a lag inherent in that process. And if we did nothing about that, then at best, we're going to have given up 40% of your potential ability to resolve high contrast imaging. You'd have motion blur if we didn't do anything about it. The second thing is if I don't fully transfer the charge, if I leave some of those photoelectrons behind, say some are still in the red when I was supposed to be moving them over to the green, then I have yet more contribution to blur. None of this sounds great. It sounds like this is a sort of approach that's going to lead me to soft images, and it's not going to faithfully reproduce what I'm after. The first one we call discrete charge transfer loss. The second one we call charge transfer efficiency. These are two critical parameters. So I want to share a little bit of the technology behind how we address that and why you can actually get high quality images out of something that seems like it should have these losses in them. So I'm going to take those pixels, I'm going to twist them on their side for a second. I'm looking at two pixels right next to each other. Your motion is in this direction here. I'm going to point out a couple things about how these pixels are actually made and some of the architectural choices which improve image quality. The first thing is this red region here, the buried channel. If you come to our more sensor specialist conferences, you'll hear our experts talking about the CMOS designs associated with this. But think of it as a highway for photoelectrons, highly optimized to make sure that when we try to move those photoelectrons from pixel to pixel, that all of them move. And to give you a sense of how much all is, we measure it in the number of nines following that decimal place. So 0.9999995 nines, 99.999% of the charge is moving along. When you do the math on that, it turns out that it has effectively now negligible impact on MTF. All of the charge is sufficiently moving from pixel to pixel.
Every drop of water.
Every drop of water, not any left behind in the bucket. So problem number one solved. The second problem is you still have discrete pixels. And if you look at the top of this photo, you will see these red structures. These are what we call the gates that are moving the charge through the pixel. And you'll notice there's more than one. For the purposes of today, what I want to identify is that we aren't just taking a bucket and dumping the whole bucket from pixel to pixel. We have ways of, at sub-pixel levels, migrating those charges in an almost continuous fashion, to the point where from an MTF impact perspective, we're well above 90% from a sort of perfect ideal scenario. So high that we'd sort of challenge you to try to measure the actual difference in a scan direction versus a cross direction in this type of device. Basically, you can get imaging as high quality as you could just dwelling with a scientific camera, as an example, at one image, that you can with this moving. When you put all that together, we package that in a standard camera that has 16,000 pixels across. The multiple arrays in there gives you over 400 stages that boosts the responsivity of your signal even as you're moving. It's backside illuminated, 2 high-speed connectors on the back. This is effectively a 200 gig camera is sort of the way you could think about this. So we have the ability to move a ton of data off of this if your application requires it. And there's an 8K version as well too, a little bit more suited for perhaps high-end microscopy where you also need very high magnifications. But what we'll sort of start to talk to you about is actually we're changing that assumption as well too, that you're actually able to get some fairly high magnification, high NA imaging out of a 16K device and getting all the throughput out of that as well. So I shall pass over at this point. Back to Kevin.
Okay. So those are among the most advanced TDI cameras in the world. And they're a very important part of the imaging system. But there is a little more. When you're going to build a microscope, there's other bits. You need precision because the field of view is considerably smaller than the sample, whether that be a DNA flow cell or a semiconductor wafer. The sample is larger than the field of view, so you need an XY stage. Focus is important, so you need a Z stage. There's servo controllers to make those axes go. You need the optics, some structure. You have to illuminate the field of view. There'll typically be an autofocus to automatically maintain focus as it moves. And then, of course, there's frame grabbers to take that massive data flow and get it into memory and save it. So here's a sort of cartoon model cut away with annotations. And this presentation will be available afterwards. Now, on the next slide, we see an actual physical example. Because it's mostly made of black metal, it's harder to kind of identify the bits and pieces, but we actually have one of these operating, doing fluorescence imaging in real time over in the other corner of this hall at booth 148. We invite you to come on over. And the system has some very effective vibration isolation. As a result, as you watch the images, we encourage you to actually kick the counter. The image quality remains unchanged. So we're going to run through here a few basic calculations of that you're going to need. And the first is to ask, what are you looking at, and what resolution are you trying to achieve? Because ultimately we scale the system to suit the resolution. And that resolution is limited by the wave nature of light through diffraction. And there's the formula, 1.22 lambda over 2Na is the diffraction limited resolution. For a wavelength of 500 nanometers and a NA numerical aperture, that's the size of the cone of light coming out of the objective, that resolution is about 350 nanometers. Now you want to oversample that by 2.5 to 3x. So in this particular example, a nice pixel would be 125 nanometers. These cameras have a pixel size of 5 microns or 5,000 nanometers. So what that says is that the optics, the objective, and the tube lens together should provide, in this particular case, a magnification of about 40. Now, it turns out that we have a partner not presenting today who booth 1049, and they have optics that does exactly this and provides a very high, very large field of view. Now, when we're clocking these at a 1 megahertz line rate, which is what they do, and the pixel is 5 microns, and the magnification is 40x, that corresponds to a scan velocity of 125 millimeters per second. So sort of going about like this. Now, with a 1G accel decel, we can get up to speed, constant velocity in all of 13 milliseconds. We only have to allow about 8 millimeters on each side to accelerate and decelerate. But we have a special capability we'll go into in a moment that means that we can actually perform the imaging from standstill to standstill. We'll talk about that in a moment. The total imaging throughput with the stock objective mentioned here is 150 square millimeters per second. And with certain custom optics, that can be as high as 250 millimeters per second, square millimeters per second. And at a diffraction limited resolution of 125 nanometers, that's an extraordinary amount of data. Now, earlier when we looked at the diagram, I mentioned that the vertical transfers, the thing that caused the rows to pour their buckets of photons to the next row, that's done by a digital signal. And where that digital signal originates is pretty important. The first thing that occurs to everybody is, oh, we'll just use a crystal clock. But it turns out that in that case, any deviation in velocity of our stage would cause both image smearing and contrast modulation. So what we do is we take the linear encoder in the stage and we use it to generate the vertical triggers. And in that case, things are essentially perfect. They're always limited by diffraction. And there's certain attributes of the encoder that are really important if you're going to do this well. There are a bunch of encoders that don't do it so well. And so I'd like to advance to one of our stage products, which is called Smart Stage XY. And this, I have a single axis version of it here. This is a pretty advanced motion control stage. The servo controller is built in. You can't see it, it's underneath that little hatch there, but there's no outside box of electronics making this thing go. It is, all you do is give it DC bus, 24 volts typically, and communication, frequently over CAN. As we'll see in a moment, the encoder cyclical error is pretty much zero. If the encoder had cyclical error, that will print through into your image, and we don't want that. The velocity ripple at 125 millimeters per second is less than 0.1%. But we also have a technique to eliminate contrast modulation. And there's another thread, which is that microscope optics, the magnification varies from unit to unit. And so we have the ability to fine-tune the resolution of the stage and therefore the distance between the triggers with an incredible granularity. If the nominal resolution of the stage is 10 nanometers, between 9 and 11, we provide 32,000 discrete resolutions. It's pretty out there. So I mentioned how good our encoder is. In this first plot, we're looking at its cyclical error. What kind of periodic error does it manifest from half of the period of the grading to 10 times the period of the grading? And all 11 orders in this case are under 1 nanometer RMS. This is optically indistinguishable. The encoder is essentially perfect. Over on the right, we've got a histogram. We're generating these triggers every, in this case, 250 nanometers, and they are what are causing the buckets to flow the charge. And there is a histogram of 480,000 individual vertical triggers, every single one of which we have used a custom in-house built laser interferometer to position stamp every one of those triggers. And as you can see, they do that 250 nanometer spacing, all 480,000 of them to a couple of nanometers. It's really quite good. Now, one thing I'd like to point out is that conventional microscope optics just doesn't cut it for large, high throughput TDI. So here is a typical microscope objective. It's made by Nikon. It's a very high quality device. It's not cheap, but conventional microscope objectives all have one foot in the 17th century, which is they were designed for eyeballs and they were meant to fill a field that would typically be an eyepiece. And that simply won't handle monster sensors like this. So one of our partners, IDEX Health and Science, have gone and done really a wonderful job last year in introducing their X-Plan series. This is a 0.88 numerical aperture objective. This is the one in the example previously, and this is the tube lens. Now, by the way, that's the actual official Nikon tube lens. It's a cemented doublet. There's a little bit more going on here, and it's there for a reason. This is what it takes to fill the field of monster sensors like this and extract all of the super high frequency information that's there. Now, we're doing time-wise. Might have to pick up the pace a little bit here. It'll all be available online, and there will be a white paper accompanying this that actually goes into my greater detail. Velocity ripple is a bit of a thing. Even though you're producing the vertical transfers from the encoder, that implies perfect spatial resolution. But if we slow down and speed up, the image gets brighter and dimmer, so there's a contrast modulation. And we basically fix that by setting the shortest interval between triggers, and our vertical transfer trigger, we control not only where it happens, but how long it stays on. And by turning the light on only for the amount of time that the fastest pulse would occur, they all get the same illumination, and that's how we can image from standstill to standstill. One last quick plug is you have to focus this sort of thing, and we make some very nice stages to do that. Now, there are some additional ancillary aspects of a TDI imaging system that we need to consider. A really basic one is that it is essential that the scan axis motion be very precisely perpendicular to the sensor axis. And we achieve this by a one-time fine rotary alignment of either the scan axis itself with fine adjustments that rotate it around theta z, or a very fine adjustment of the camera. And that's a one-time set and forget. Now, there's another important alignment aspect, which is that the sample plane needs to be precisely perpendicular to the optical axis. If you have a flat sample, that's pretty easy. You simply do a one-time leveling. It's a set and forget in tip and tilt. But in other cases, the sample is somewhat warped. We refer to this as potato chipping, and that can be a challenge. One way to address this is to use a precision ground vacuum chuck, which pulls the sample flat. But even in that case, there are situations where there will still be some residual warpage of the sample. Now, there's two kinds of warpage. One would be warpage in pitch, which is rotation around the step axis. Think of waves along the scan axis. And that really isn't all that hard because it's automatically compensated by the autofocus system, which is moving the focus objective stage up and down. So that's easy. However, warp in roll, which is rotation around the scan axis, is a different matter altogether. And the autofocus can't fix this. It can focus on the center of the swath, but it can't, at the same time, keep the two ends of the swath in focus. That's where it gets a little tricky. One solution is to add a tilt stage, and in the simplest case, you would perform a once per swath static but motorized tilt correction. But in other cases, especially if you're dealing with wide swaths, which is big sensors and big optics, you may need to perform dynamic roll correction during each scan. And we provide stages that can do this. And last little bit of detail to go into here is short range straightness. So as we scan along the axis, it's critical that we do so in a very straight fashion. Any lateral jitter that is motion left to right as we're scanning along the axis will degrade the image quality. And this is especially critical over the very short distance corresponding to the depth of the sensor. The higher the number of rows in the sensor, the larger. But then again, it's transformed by the magnification, so it's smaller down at the sample. Now, common motion technology is recirculating or profile rail bearings. They're actually very bad for TDI because they have intrinsic lateral jitter, also vertical jitter, which happens when the balls and rollers enter and exit the preload zone. Recirculating guideways should not be used for TDI. Crossed rollers work quite a bit better, and air bearings even better yet. Although the smaller crossed rollers of a certain brand, which have a stud roller, that stud roller actually prints through and produces some lateral jitter. So you have to be careful whose brand you choose and what size it is. Now, we typically measure short-range straightness by directing the beam of a laser interferometer at a flat mirror, long flat mirror that runs the length of the scanning stage. And we run the stage at scan velocity and measure the straightness. The resulting high-resolution straightness data we then process using a boxcar filter that rolls and samples every series of points along it. We then apply a best fit straight line to that data, but we do so over a characteristically short distance, typically 0.5 millimeter to 1 millimeter. Our cross-roller TDI scanning stages typically achieve short-range straightness of about 5 nanometers per 0.5 millimeter. Our air-bearing stages offer even higher performance. However, they require clean, dry air for operation, and not every end user can supply that. Now, we've covered a lot of detail today on the aspects of a TDI microscopy system. The takeaway we'd like to leave you with is that if you just go buy a TDI camera and try to do this all on your own, unless you've got a really experienced team, there's a lot of pitfalls. But the good news is we've got you on this. Between the camera partner, the motion partner, and the optics partner, we've done this a number of times. We know all the little gotchas, and work with us, tell us what you want to do, and we will get you to the finish line much faster and much more efficiently by virtue of that experience. So with that, I'll turn it back over to Mike for some wrap-up slides.
Thank you, Kevin. We're sharing with you what's really decades of innovation. And one thing that we really want to kind of leave as a point to you is that all of that experience and know-how for at least a half century for both of our companies, I think even a little longer for Dover's, is all been brought forward to today in what you see here, which is a standard set of products and the know-how to be able to put that to use. Our goal is to help reassure you that the technology has been well proven, well tested in the most demanding of applications in order to get the kind of image quality that you're after, and that we continue to innovate and bring enhanced capabilities to these products day in, day out, year after year. So rest assured, what you see here from a standard perspective is in many ways just the sort of tip of the iceberg. If you asked questions about your specific application, how much faster can you go? Do I need everything here? What if I want something that's really quite tailored to my application? I want my own pixels. I want my own custom motion. A significant part of both of our businesses, indeed our optics partners as well too, is entirely that. Teledyne, we own our own fabs for CCD. We have extensive fab relationships around the world to help produce our products. We design all of this ourselves. So we are, if you will, silicon right through to the digital image data sitting in your GPU, as an example. We have that whole path covered. And with Dover Motion, we have all aspects of the motion covered as well too. So that ecosystem is fully something that we can control and manage. And if there's something unique that you're looking for, absolutely, we can provide it. From a customization perspective, I'll say the specs and performances that you've heard here today, like I mentioned, are the tip of the iceberg. There is significantly more horsepower and capability if you need and want to have a custom conversation to make sure you got the differentiation needed for the products that you might make. So to wrap up, so long as you're not dwelling in your image staring, let's say, at the stars in an astronomy-like application, or perhaps you need 15 seconds exposure or 3 hours of exposure. As soon as you start to get into milliseconds, tens of milliseconds, even some cases hundreds of milliseconds worth of exposure, you're into a regime where this approach is going to beat that for throughput. And of course, the more light you have, or the shorter you can manage from an exposure time, then the better this gets. And we have tricks, as we've discussed, to help shift that point ever so increasingly into the favor of TDI scanning to solve your throughput. And I hope that through today, we're helping address some of those questions around, is this a compromise in quality? Am I taking speed over quality? No. Certainly, we have many applications with partners who are showing their instruments here today that achieve both. And of course, if you're new to this, and if some of what we're talking about is fresh to you, or it sounds a little intimidating to set up a practical experiment on your benchtop to see how it works in your application, phone a friend. We have extensive experience setting this up quickly and easily. It is not uncommon for partners that are brand new working with us to have a test bench set up in a day to be able to demonstrate the kinds of capabilities that we're talking here about as well too. So without further ado, we'll wrap up at this point, but say we're here to speak with you after. If anybody would like to continue to chat, you can find Dover at booth number 148. You can find Teledyne at booth 427.
And IDEX at 1049.
Excellent. Thank you very much. We appreciate your time and attention, everybody. Look forward to TDI scanning with you in the future. Thank you.